Hello, I'm Hank. I assume that you are here because you are interested in biology. If you are, that makes sense because like any good 50 Cent song, biology is just about sex and not dying. And everyone watching this should be interested in sex and not dying, being that you are, I assume, a human being. I'm going to be teaching this biology course a little differently than most courses you've ever experienced. For example, I'm not going to spend the first class talking about how I'm going to teach the class. I'm just going to start teaching the class, starting right after this next cut. First, I just wanted to say if I'm going too fast for you, the great thing about me being a video and not a person is that you can always go back and listen to what I've said again. I promise I will not mind. You are encouraged to do this often. A great professor of mine once told me that in order to understand any topic, you only really need to understand a bit of the level of complexity just below that topic. The level of complexity just below biology is chemistry, or if you're a biochemist, you would probably argue that it's biochemistry. So we need to know a little bit more about chemistry, and that is where we're gonna start. I'm a collection of organic compounds called Hank Green. An organic compound is more or less any chemical that contains carbon, and carbon is awesome. Why? Lots of reasons. I'm gonna give you 3. First, carbon is small. It doesn't have that many protons and neutrons, almost always 12. Rarely it has some extra neutrons, making it C13 or C14. Because of that, carbon does not take up a lot of space and can form itself into elegant shapes. It can form rings, it can form double or even triple bonds, it can form spirals and sheets and all kinds of really awesome things that bigger molecules would never manage to do. Basically, carbon is like an Olympic gymnast. It can only do the remarkable and beautiful things it can do because it's petite. Second, carbon is kind. It's not like other elements that desperately want to gain or lose or share electrons to get the exact number they want. No, carbon knows what it's like to be lonely, so it's not all, I can't live without your electrons, needy like chlorine or sodium is. This is why chlorine tears apart your insides if you breathe it in gaseous form, and why sodium metal, if ingested, will explode. Carbon though? It wants more electrons, but it's not gonna kill for them. It's easy to work with. It makes and breaks bonds like a 13-year-old mall rat, but it doesn't ever really hold a grudge. Third, carbon loves to bond because it needs 4 extra electrons, so it will bond with whoever happens to be nearby. And usually, it will bond with 2 or 3 or 4 of them at the same time. Carbon can bond to lots of different elements: hydrogen, oxygen, phosphorus, nitrogen, and other atoms of carbon. It can do this in infinite configurations, allowing it to be the core element of the complicated structures that make living things like ourselves. So because carbon is small, kind, and loves to bond, life is pretty much built around it. Carbon is the foundation of biology. So fundamental that scientists have a hard time even conceiving of life that is not carbon-based. Silicon, which is analogous to carbon in many ways, is often cited as a potential element for alien life to be based on, but it's bulkier, so it doesn't form the same elegant shapes as carbon. It's also not found in any gases, meaning that life would have to be formed by eating solid silicon, whereas life here on Earth is only possible because carbon is constantly floating around in the air in the form of carbon dioxide. Carbon, on its own, is an atom with 6 protons, 6 electrons, and 6 neutrons. Atoms have electron shells, and they need or want to have these shells filled in order to be happy, fulfilled atoms. The first electron shell, called the s orbital, needs 2 electrons to be full. Then there's the second s orbital, which also needs 2. Carbon has this filled as well. Then we have the first p orbital, which needs 6 to be full. Carbon only has 2 left over, so it wants 4 more. Carbon forms a lot of bonds that we call covalent. These are bonds where the atoms actually share electrons, so the simplest carbon compound ever, methane, is carbon sharing 4 electrons with 4 hydrogen atoms. Hydrogen only has 1 electron, so it wants its first s orbital full. Carbon shares its 4 electrons with those 4 hydrogens, and those 4 hydrogens each share 1 electron with carbon, so everybody's happy. This can all be represented with what we call Lewis dot structures. Gilbert Lewis, also the guy behind Lewis acids and bases, was nominated for the Nobel Prize 35 times and won none. This is more nominations than anyone else in history and roughly the same number of wins as everyone else. Lewis disliked this a great deal. He may have been the most influential chemist of his time. He coined the term photon, he revolutionized how we think about acids and bases, he produced the first molecule of heavy water, and he was the first person to conceptualize the covalent bond that we're talking about right now. But he was extremely difficult to work with. He was forced to resign from many important posts and was also passed up for the Manhattan Project. So while all of his colleagues worked to save his country, Lewis wrote a horrible novel. Lewis died alone in his laboratory while working on cyanide compounds after having had lunch with a younger, more charismatic colleague who had won the Nobel Prize and worked on the Manhattan Project. Many suspect that he killed himself with the cyanide compounds that he was working on, but the medical examiner said heart attack without really looking into it. I told you all that because, well, the little Lewis structure that I'm about to show you was created by a deeply troubled genius. It's not some abstract scientific thing that has always existed. Someone somewhere thought it up, and it was such a marvelously useful tool that we've been using it ever since. In biology, most compounds can be shown in Lewis structure form. And one of the rules of thumb when making these diagrams is that some elements tend to react with each other in such a way that each atom ends up with 8 electrons in its outermost shell. That's called the octet rule, because these atoms want to complete their octets of electrons to be happy and satisfied. Oxygen has 6 electrons in its outer shell and needs 2, which is why we get H2O. It can also bond with carbon, which needs 4, so 2 double bonds to 2 different oxygen atoms, you end up with CO2, that pesky global warming gas, and also the stuff that plants and thus all life are made of. Nitrogen has 5 electrons in its outer shell. Here's how we count them. There are 4 placeholders, each wants 2 atoms, and like people getting on a bus, they prefer to start out not sitting next to each other. I'm not kidding about this, they really don't double up until they have to. So we count it out. 1, 2, 3, 4, 5. So for maximum happiness, nitrogen bonds with 3 hydrogens forming ammonia, or with 2 hydrogens sticking off another group of atoms, which we call an amino group. And if that amino group is bonded to a carbon that is bonded to a carboxylic acid group, you have an amino acid. Sometimes electrons are shared equally within a covalent bond, like with O2. That's called a nonpolar covalent bond. But often one of the participants is more greedy. In water, for example, the oxygen molecule sucks the electrons in and they spend more time around the oxygen than around the hydrogens. This creates a slight positive charge around the hydrogens and a slight negative charge around the oxygen. When something has a charge, we say that it's polar. It has a positive and negative pole. So this is a polar covalent bond. Ionic bonds occur when instead of sharing electrons, atoms just donate or accept an electron from another atom completely and then live happily as a charged atom or ion. Atoms would in general prefer to be neutral, but compared with having the full electron shells, it's not that big of a deal. The most common ionic compound in our daily lives, that would be good old table salt, NaCl, sodium chloride. But don't be fooled by its deliciousness. Sodium chloride, as I previously mentioned, is made of 2 very nasty elements. Chlorine is a halogen, or an element that only needs 1 proton to fill its octet, while sodium is an alkali metal, an element that only has 1 electron in its octet. So they will happily tear apart any chemical compound they come in contact with, searching to satisfy the octet rule. But no better outcome could occur than sodium meeting chlorine. They immediately transfer electrons, so sodium doesn't have its extra, and the chlorine fills its octet. They become Na plus and Cl minus and are so charged that they stick together, and that stickiness is what we call an ionic bond. These chemical changes are a big deal, remember. Sodium and chlorine just went from being deadly to being delicious. There are also hydrogen bonds, which aren't really bonds so much. So you remember water? I hope you didn't forget about water. Water is important. Since water is stuck together with a polar covalent bond, the hydrogen bit of it is a little bit positively charged and the oxygen is a little negatively charged. So when water molecules move around, they actually stick together a little bit, hydrogen side to oxygen side. This kind of bonding happens in all sorts of molecules, particularly in proteins, and plays an extremely important role in how proteins fold up to do their jobs. It's important to note here, bonds, even when they're written with dashes or solid lines or no lines at all, are not the same strength. Sometimes ionic bonds are stronger than covalent bonds, though that's the exception rather than the rule, and covalent bond strength varies hugely. And the way that those bonds get made and broken is intensely important to how life and our lives operate. Making and breaking bonds is the key to life itself. It's also like if you were to swallow some sodium metal, the key to death. Keep all of this in mind as you move forward in biology. Even the hottest person you have ever met is just a bunch of chemicals rambling around in a bag of water. And that, among many other things, is what we're going to talk about next time.
After threshold 2, the universe had lots of stars, but most of space was still cold, dark, and mostly empty. The universe consisted almost entirely of two types of atomic matter, hydrogen and helium. These were both light gases, and one of them was totally inert. Like a painter with just two colours, one of which won't mix, it was impossible to make anything very interesting. The universe needed more colours, more chemical elements, and that was the work of threshold 3. Making new elements meant fusing more protons and neutrons together. To do that, you needed very high temperatures, which could only be found inside massive stars that were aging or dying. Only they have the right Goldilocks conditions for threshold 3. Why? Well, large stars have so much mass that they can create enormous pressures and temperatures. Those temperatures get cranked even higher when large stars run out of hydrogen. When that happens, fusion stops at the centre and the star collapses like a burst balloon. If the star's big enough, the collapse is huge, creating such high temperatures that helium nuclei can fuse into nuclei of carbon. When the star's used up its helium, it collapses again, and the cycle starts over. The star heats up and starts to fuse carbon to form oxygen. It collapses again, then does the same to create other elements like silicon, nitrogen, and eventually iron. If it's a really, really big star, it'll finally die in what's called a supernova. That's an explosion so hot and so energetic that, for a while, it'll shine like an entire galaxy, and it'll produce enough heat to form all the other elements of the periodic table. Then the supernova scatters these new elements into space, and voila! We have a universe with lots of different elements. Threshold 3 was crossed for the first time when the first large star died. And it's still being crossed today, as billions upon billions of large stars die, scattering the raw materials needed to build wondrous new forms of complexity.